Floods are quite unpredictable, and current flood maps have some flaws. One of their biggest flaws is the lack of consideration towards pluvial flooding, precipitation flooding that can turn into a flash flood. Urban areas are the most affected because the precipitation cannot absorb into impervious surfaces. There is limited research on pluvial flooding, since urban infrastructure varies from city to city. So when the flooding happens, the residents are ill-informed. Using the Globe Observer database and QGIS analysis tools, we developed a model that will help predict areas in Houston, Texas, that are at high risk for pluvial flooding to better inform the residents in the area.
To generate accurate and clean data that can be fed into the 3D model simulator, we use the AOI points that contain images of the north, west, east, and south of various points in the area. In order to extract the important slope data that we wanted to get, we ran a series of steps. First, we performed semantic segmentation using the UNet architecture. This segmentation algorithm separates the ground from all other objects. Once we've identified the ground, we run a SIF detection algorithm that gives us a series of points in the image. In order to get the 3D information of these points, we run a monocular depth estimation algorithm, Zoe depth, which also gives us a 3D mesh reconstruction. Finally, we interpolate the points around the features, ultimately building a dataset of elevation nuances on the ground.
Using QGIS, we can create a DEM, or a digital elevation model, with the data taken from the AOIs to simulate the flash floods on. The AOI data points, however, only cover a small percent of the area needed to make an accurate simulation. As such, we can use the Open Topography plugin on QGIS, and from a DEM of the Houston area, we can take around 10,000 elevation points, as you can see in the top left picture. X is longitude, Y is latitude, and Z is elevation. We can use this to interpolate it with the AOI data. Afterwards, we can use TIN interpolation to create a DEM using the satellite points and AOI points, as you can see in the bottom right.
To analyze the DEMs, we applied a Python D8 flow algorithm. The D8 flow algorithm determines the flow direction based on the direction of steepest descent at each elevation cell and assigns an 8-bit integer based on the shown grid. East is 1, southeast is 2, and going counterclockwise around, we multiply by 2 each time until we arrive at 128 for northeast. For instance, if the steepest descent from a cell is northwest, shown in the green, it gets the direction code 32. A benefit of this labeling system is also that it allows for combining multiple directions of equal descent. A cell flowing equally northeast and southeast, shown in blue, will get the value 130 because of 128 for northeast is added to 2 for southeast. This way we can represent flow out of a cell using a single 8-bit integer for each cell. To illustrate, consider a 5x5 elevation data table on the left. Arrows in each cell indicate the steepest descent direction, indicating water flow. On a corresponding table on the right, cells are relabeled based on their flow direction codes. The main goal of this is to measure flow accumulation, which indicates how many cells contribute flow to a specific cell. For example, this cell's value of 17 on the accumulation plot indicates that 17 cells worth of water are flowing into this one cell, showing where water will pool in case of a flash flood. Using Google Colab, we applied this D8 flow on the Houston AOIs, then plotted it using Python's matplotlib. In this example, AOI 3 in Houston, the left graph shows a standard elevation graph using the raw elevation data from the DEM. On the right, the graph shows a color-coded direction map, where each color represents a different direction code from 1 to 255. Finally, these two graphs depict the flow accumulation in both linear and logarithmic color bars. Here, for this specific AOI, we can observe that the water seems to pool in the roads.
In order to make this tool accessible, we made a website that allows users to select areas in Houston to simulate the flash flooding on. We used Flask for backend development in Python. The AOI points for Houston were imported via a CSV file into a SQLite database. The Flask application used SQL queries to retrieve the points from the database. Users could select and deselect points on the map. This feature was added in the front end with leaflet.js. After confirming the points, a DM of the selected points would appear on the website, and users could simulate flash floods on the model, which would reflect how flash floods would occur at that AOI location. The website is a very useful tool to publicly implement the resource we created and aid with flash flood preparation for those living in that AOI area.
With this tool, users can see which areas have high risk of flooding in Houston, Texas. Since we can also simulate the flowing of the water as well as where it will end up, this tool will allow developers and homeowners to keep themselves safe. In the future, this research can be expanded on to make this more general, so every developed area in the country can go through flooding simulations. The limitations of this project can also be improved on, as the accuracy of the civilian-taken data in the form of AOIs and QGIS's plugins lends the project a degree of inaccuracy. As such, in the future, more reliable tools and data can be used in order to make more accurate DEMs to run simulations on. We would like to thank our peer mentors and teachers for guiding us throughout our research and our internship. Thank you for all your support.